ровно как G большого друга нашего. Вот. Одного из самых интересных математических современных. Он будет нам рассказывать про точки Хегнера на эллиптической кривой. Один из его, я понимаю, любимых сюжетов, но у него их тут 20, так что это... Вот. И прошу, значит, наслаждаться замечательным докладом. Bring it down. You're welcome. You lost your paper?
No, I wasn't yet prepared to the morning. So, thank you.
Sorry.
Then I have more time to prepare. Na каком языке я собираюсь говорить? И ответ, конечно, по-английски. Не могу. Название доклада по-русски. Я не выбирал, а Василий Голышев писал только Хейгнера. Я бы сказал, скорее точки Хейгнера новые точки зрения. So I write in English, although the joke doesn't work in English. All Heegner points, new points of view. So I want to talk, this is partly as kind of preparation for lectures that hopefully will be given here in coming months by other people connected with the theory of Heegner points. So I was asked if I could talk on this subject. This is for me, very old work, and I've essentially nothing new to say. But I'll try to review the old work, which is from something like 1985, with Dick Gross, some other people. And then I give background and also some things that happened later in the last 30 years. What does this do? Ah, right. Yeah. So, I don't know what people's background is. I want to talk about Heegner points, well, as the title said, on elliptic curves. And the first thing that should be said about them is that they don't exist, because Heegner points are not on elliptic curves at all. Heegner points are on modular curves. But luckily, there was a conjecture, which is now a theorem, that above every elliptic curve is a modular curve. And so if the Heegner point is here, there is in fact a Heegner point here. So I'm going to begin by reviewing these basic definitions, and I want to do it using an example, because almost every general statement is exactly as easy to understand in the example as in general, but the example makes it more alive, and then one sees exactly what it says. So I'm interested in the elliptic curve. over Q. So an elliptic curve, well, it's a curve, so it's a one-dimensional object, and it's also got a group action. So there's one point which is the origin of the group, and then it's a theorem which is very, very old, that such a curve can always be put into some standard Weierstrass form. There are many other forms, but this is one form, x cubed plus ax plus b, where, let's say, a and b are the irrational inputs to keep things simple. So every elliptic curve over Q has an equation like this, and let's just take this to be the definition for the moment. And I assume that the discriminant is non-zero, so the cubic on the right has three distinct roots. So the basic fact about an elliptic curve, if you draw the graph, let's say over the real numbers, it might look like this, or, well, it might look like this, or it might look like this. But the basic fact, which I'm sure everyone has seen, since it's given by a cubic equation, actually for this it doesn't have to be Weierstrass form, it could be any cubic equation. For instance, this equation, the Fermat equation, would be also an example. But because it's cubic, if I have a straight line, it will intersect the elliptic curve always in 3 points, maybe something complex. For instance, this line would be complex points. And therefore, if I have a point here which has coordinates, let's say in the rational numbers or in some field k, which I've chosen, and if this other point also has coordinates in the same field, then this line goes through 2 points with coordinates which are in k, so the slope is in k, and then you see immediately that the third intersection point is also in k. If an equation with coefficients in field k has 3 roots, and all but one of them, or 2 of them, are rational in that field, then the third is rational. And then you just decide that if these 3 points are called P and Q and R, then you have P plus Q plus R is 0. So you have a group law, which is not obvious from the equation, but that was actually my initial definition. It was a curve with a group law, so I've more or less said why this has such a group law. So now in number theory, what you do is that you say we're interested in the number field, let's say in the rational numbers, but it's too hard to study directly. And so what one does is one says that there are connections between this and various other fields. For instance, Q can be put into the real numbers or into the complex numbers. And so we can take this equation, A and B are certainly also real numbers and complex numbers. And so we can think of the curve over the reals or over the complex. And I already did that when I drew this picture. This picture shows the real points. And the notation people use, of course, is E of k, or for any variety, x of k is the points with coordinates in that field. So what I've drawn here is E of r. And it's a one-dimensional curve in the usual sense. But I can also look at E of c, which would be a torus. But I can also look, for instance, the field of 3 elements. By taking this equation with A and B and C, and just considering it as an equation modulo P, which is computes A and B and also x and y in some sense modulo P. So let's take an example and look how these different things look. So the example will have to do with the number 37. But you won't see the 37 for a while. In the example, it will be invisible. So the equation of the curve that I'm going to take, it's a very simple one. This is my basic example. Is this equation, y times y minus 1 equals x times x minus 1 times x plus 1. So of course I can write this as y squared plus 4 is x cubed minus x. But that's not quite in the form I told you, but now if I multiply by 4, and add 1, and if I make a slight change of variables, if I set 2y plus 1 equal to y1, now it is in this form, well, almost, it's the coefficient 4, which, so there'll be some extra 2's in some of the formulas. Sorry? Certainly plus 1. Oh, here, this one is minus 1. Thank you very much. So 1 point, is that you? Who said that? I didn't hear who said minus 1. Was it you? Okay. So everybody who can correct me gets 1 point. So far he's the winner of this game. And I usually make about 1 mistake a minute. And I've been told that 1.5 hours, so everybody should get at least 1 point. So you started, thank you very much. Okay, but it's very small. For a big mistake, you get 10 points. But you don't opportunities over this too.
what are the relation? What is the relation between the two equations?
Which two equations? They're equivalent. If I take this equation,
Yeah.
multiply it by 4 and add 1, then I get this equation, which is the same.
Yeah.
They're simply the same, and then if I complete the square, this is y1 squared. So all I've done is put it in standard Weierstrass form. So the standard Weierstrass form, but it's not as beautiful, because if I look at the equation 4x cubed minus 4x plus 1, I think nothing. I see nothing. But if I look at this equation, I say, oh, this is a nice curve. I see many points. Let me draw a picture. Actually, I should have prepared it. Of course, I didn't, but I'll do my best. You see, the picture will not quite have the symmetry I said here, because here y goes to minus y, which is actually sending the point to its negatives. And here, because my y is not really y1, but y1 plus a half, the symmetry line would be at the level of half. But now you see in this original coordinates, which are more convenient, you see a point here, 0, 0. Obviously, if x is 0 and y is 0, this equation is true. But also if x is 1. If x is 1 or if x is minus 1 and y is 0 or 1, then both sides are 0. So we immediately see, without any work at all in this example, 6 points. Which is already a good sign, because what we're doing here is arithmetic, so Diophantine equations. In this case, we're looking for solutions, and we already have 6 that you can see right away. So let's take this curve and do what I said, which is to consider it over the rational numbers, and over the complex numbers, and over the real numbers, and over the numbers multiple p, and see what this gives us. So I'll look at my notes, since I don't know in what order. So well, let's start over q. So first my field is q, which is the most difficult. But I can start with that. So, well, maybe I'll put that here. So E of q contains at least these 6 points that I just drew. But actually it's a theorem. Remember, I told you that you can add points. For instance, the sum of these points. Well, remember I said if 3 points lie in a straight line, their sum is 0. So the sum of these points is minus this point. And I also said that the negative of the point is the reflection. So the sum of these 2 points is this point. So we see the beginning, and now you can keep adding these points, and you'll get new points. And in fact, let me give you a little list, if I can find it. Unfortunately, I meant to take 2 minutes to organize my pages before I came in. I don't see where I have the table here. So let me take this point. I'll call this one here P0. So I'll make a little table here on the left. P0 is the origin. And now I take 2P0. So for 2P0, I have to take the tangent line at this point. And I think it goes through this point, and then the reflection will be that, so it should be the point 1, 0, and indeed that's what my notes say. Now I take 3P0. So this is P0, this is 2P0. If I add them, then this would be minus 3P0, and therefore this is 3P0. So therefore 3P0, but seem to have made a mistake. That's right, no, it's minus 1, 1. That's exactly what my notes say. And now if you do it a couple of more times, you find this. I'm not writing the negatives, because every time I have one of these 6 points, the reflection in this axis is the negative. So minus 4P0 would be 2 minus 2. But this is a point we already didn't see in my picture. If you go on to 2 and 3, then you can check that 3 times 3 minus 1 is 2 times 1 times 3. I hope it's correct. And so that's also a point. And similarly, 6P0 is a point that we didn't immediately see. All of these were integer points. And in fact, I think that's all. There may be one more. But it's a theorem that for any such equation, the number of points with integer points is finite. It's not a very hard theorem. It's certainly not a trivial theorem either. But that means that in general, if I do this, I will not have integer points, I'll have rational numbers. And here's the first example in this table. Okay? So I'm going to need those points in a minute to continue with my example. So that's the first field that we looked at. We saw that, and in fact, here's the theorem. The theorem of Mordell, proved in around 1920, I think, I don't remember the exact date, said this for any elliptic curve, like here, that this group is always a finitely generated, well, it's abelian, that's true for any elliptic curve, It's a finitely generated abelian group. And a finitely generated abelian group always has the same form. It's z to the r, so z plus z r times for some r. And then we have a finite group. Now this finite group is very restricted. It's very elementary to show that it's either a cyclic group or the product of a cyclic group of two cyclic groups, one of order 2 and the other of even order. But in fact, there are only 12 possibilities for this group. That's a very deep theorem of Maser. But I don't care. Let me call this particular curve, just to avoid confusion, E0. Then in my particular example, the rank is 1. And in fact, this is the simplest example with rank 1. Rank 1 means that there are infinitely many points. And we already saw that there are quite a few, and it's not repeating. It seems pretty clear that if I keep doing this procedure, I will get infinitely many points. And it's true, and in this case, there's no torsion at all. And so in this particular case, it's particularly easy. This group, which is called the Mordell-Weil group, even though it's Mordell's theorem, the reason is that this theorem, as I've stated, is only for elliptic curves over Q, and was later generalized by Weil to arbitrary abelian varieties over arbitrary number fields with the same right-hand side, still a finitely generated abelian group, but for elliptic curves over Q, it's Mordell. And here the group is just all multiples of P0. So that's the first of my many fields. But then we want, when you do any kind of mathematics, you need invariance. And so we need an invariant which tells us whether there are a lot of points or a small number of points. So that means first you want to know what this rank R is, and that's the Birch-Smith and Dyer conjecture. I'll come to it in a few minutes. But you also want to know whether the points are big or small. So you see this point, P0, had very, very small coordinates. I mean, you can say 0 is a small number, but it also is a small numerator and denominator. It doesn't require a lot of ink or chalk to write it. So this is a point of what's called very small height. So it's like me, I have very small height. And the height is a number that you can associate to a point on the elliptic curve. It's a positive number. And it's quadratic. So if you take 2 times the point, the height will be 4 times as big. If you take 3 times the point, so whatever the height is of P0, it's some number. Then the height of this is 4 times that number, 9 times that number, 16, and so on. So in order to have many, but the height roughly tells you how much chalk you need. So this is still small, but it's not as small as this. It's getting a little bigger. And so the height of a point is a measure. It's greater than or equal to 0, and it measures the complexity. And it has the property that I just said, that if you multiply a point by n, you multiply the height by h. And now I can actually give you a definition of the height. The height of the point is equal, I'll put it on in a second, it's what's called the naive height plus a bounded error. So, well, if you know the notation O1, I'll just put O1, otherwise bounded. So, log of the naive height is this. If P is a point on E of Q, then it has coordinates x over y, and you can write x as some numerator divided by some denominator. So some coprime numbers and also y, but we don't need them both. And then this is just the maximum, or the sum, it doesn't really matter, well, maximum maybe, maximum of the numerator and the denominator. So if the numerator and denominator have 20 digits, then the log of a 20-digit number is about 50, then its naive height would be about 50. But the actual height is not exactly this, because that would not have this property, but it's this plus O of 1. So that uniquely determines it, because if I want to know in my example what is A to P0, then I compute on my computer 100 times P of 0. And what I'll find will be approximately, it'll be about 511, roughly. I didn't do it, but I know that. And so since I know that this is exactly 100 squared times the height of P0, I mean here there's an error, but this error is bounded. Let's say here I think it's less than 2, let's say. So I know that it's between 500 and, you know, the true height is this approximate height. So I don't know what this number is, I didn't do it on my computer, let's say it's 513. But it's going to be approximately that. That would just be the log of the number of, so it's the number of digits in base E, so to speak, of the numerator and denominator. But then since I know that this is 100 squared times this, it tells that the actual height is actually 0.05, approximately 13. And the actual number is 0.511114082. And so you can calculate it to any desired degree of precision. So this height is a measure of complexity, defined in this way. And there's a formula for it, and just for fun I'll give you the formula that you can actually compute it to any precision if you want. So in this particular case, you would start with the following. I start with t1 is 1, and then ti plus 1, it's going to be a sequence of numbers given by recursion. I take 1 plus ti squared minus 2ti cubed plus ti to the fourth, divided by, well, the denominator you might have guessed. If you look at this expression, you'll see it's almost exactly the same as the equation of the curve. 4y cubed minus 4y plus 1. So the ti is actually, I believe, 1 over the y coordinate of 2 to the I times p0. So I take my initial point, I keep doubling it, and every time I double it, I get a new y coordinate, and it will be given by this inductive formula. So this computes the y coordinates of these points, and then the height, which I gave the numerical value, just the formula of Tate, is the sum I from 1 to infinity, 1 over 4 to the I plus 1, times the log of the numerator of that expression that I just got. So, I mean, this is not important, but Tate found that there's an explicit way to compute exactly this number, which I gave you by only giving an approximate formula, that it's this elementary thing plus O of 1, and then by multiplying your point by n and taking the limit, you get a number, but if you do that intelligently, you get this closed formula. Okay, so that's one of the ingredients of what we're going to do.
Good.
Yes?
Sorry, what is H0?
Sorry?
H0 is the last formula.
Oh, typo. Half a point for that. It's only this trick. Okay, thank you. So now let's take some other things. Well, let's look at it over the reals. So over the reals, I should draw the graph, so I now take HVR. The graph of this I already drew, it's still here. This curve so it has two components. If you think of it as a group, you should think of it as the product of a circle, which is a group times the group of order 2. So as an abstract group, it's that group. And so if I do that, then I see some interesting numbers. And the number that I'm particularly interested in, let me call these 3 roots. Is there chalk the numbered color? Yes. Let me call the 3 roots of this equation 4x cubed minus 4x plus 1. Let me call them alpha, beta, and gamma. Okay? Then you have what's called the real period. And that will play a role in a second, so you'll see this number occur in the conjectures. So I need it. And it's the number, I define it as follows. I take the real points of this elliptic curve, which is this curve, but only the main component, the one that goes through the origin. The origin of this curve is at infinity. So I take just that part. And then I take my basic form, which is dx divided by the square root of y1. Remember, y1 is 2y1 minus 1, as I now know. And so if I write that explicitly, that would be 2 times the integral from gamma to infinity of dx over the square root of 4x cubed minus 4x plus 1. So this is so-called complete elliptic integral, and you can compute it, of course, numerically on these days. Split second one. And you get something, okay? Sorry, you do get something. If you don't get that, that's from the next line. I get a point. Okay, so you get this number. Just for fun, I'll mention that, so we take these same roots that I have here, gamma, alpha, and beta, and I take the square root of gamma minus alpha and the square root of gamma minus beta. And then I take what's called the Gauss arithmetic geometric mean. Just for curiosity, who has heard of the Gauss arithmetic geometric mean? And who has not heard of it? The sum of the hands is much less than the number of people. Okay, so some people don't have hands or an opinion. So just to remind you very briefly, Gauss studied this. And the Gauss arithmetic geometric mean, you have two numbers and you want the average. And so there are two possibilities. You take a plus b over 2, that's the arithmetic mean, or you take the square root of the 2. And now those are much closer than a and b were. And so if you do it again and again and again, it converges. So one way to say it is that it won't change if you make this procedure. And if the numbers are equal, then it's just the number itself. So this mean that you get by iterating this procedure, start with a and b, take a plus b over 2 and square root of a, you do it many times, it converts very, very, very quickly to a number called the arithmetic geometric mean. And Gauss's great discovery was that this mean can be given by a formula, and pi over the mean is an elliptic integral. And so in this case, this is the formula. You can compute that to 1,000 digits in 1 second on any computer, because the number of digits doubles every time you do one more step. So it goes very, very fast. Okay, so that's over R. But usually in algebraic geometry, and also here, you get a much clearer description. Everything's much simpler over the complex numbers than over R, because they're algebraically closed. So now I take k equals c. And now what we find is that the complex points of E can be identified with C multiple a lattice. So first I'm going to the second number, which I'll call omega 2. Omega 2 is defined just like omega 1, but for omega 1 I integrate my form dx over y squared root dx over ha. All of you missed a chance to get a point. It's dx over y1, not the square. It's the square root of 4x cubed, but it's y1. But you don't get a point because I noticed it. Okay, so omega 2 is the same thing, but instead of integrating from gamma to infinity, but you couldn't integrate from alpha to beta, but you'll get the same thing because in the group law, this curve is just a translate of this curve. But we can also integrate between beta and gamma. So I do the same thing that I did before, but now I go from beta to gamma, dx, again 2dx with the square root of 4x cubed minus 4x plus 1. But in that region, y is pure imaginary because this is negative. So this number, that's the one I wrote before by accident. Times I. So this second, that's called the second period. This was the real period. That's the imaginary period. This is, in this case, a pure imaginary number. And now what you can do is this. You have omega 1, which is approximately 3, and omega 2, which is approximately 2.5 times I. And so together they span a certain lattice. Okay? So here, for instance, is omega 1, and here's omega 2, and here's omega 1 plus omega 2, and here's 0 and minus omega 1, and so on. And now if you divide the plane by that lattice, you'll get a torus, which in this case is just this torus, so some kind of a torus. Then this is the set of complex points. And the way that you do that, I'm sure many of you, all of you have seen this, is to take the Weierstrass P function. So you take this lattice, I'll just call it L, lambda to this lattice, Z omega 1 plus Z omega 2, so it's a lattice in C. And then you take the Weierstrass P function for it, which maybe I won't even repeat the definition, and you take this to be your y, your x, and y will be p prime of z and lambda, and then it's just a derivative of the Weierstrass P function, which I won't write down the definition, and then it's a standard theorem due to Weierstrass from the 19th century, that y squared is a cubic polynomial of x for any lattice, and for this lattice, it's this cubic polynomial, 4x cubed minus 4x plus 1. So this gives an explicit way to identify the complex points of E with this lattice. And the real points of E would be this real line, which is actually a circle, because when you go from here to here, and on the torus that becomes a circle, but also the points applied to half. Those would also be real, because the complex conjugate at this point is here. But this point is the same as that point up to the lattice, and so it's equal to its own complex conjugate, so it's a real point, even though in the complex plane it looks half imaginary. Just as an example, the point P0, which was my generator of the rational points, in this picture is about here. So under this map, P0 will correspond, I have it written down somewhere, it's about minus 0.09 times omega 1, I forget the exact number, plus a half omega 2. So it's somewhere off here on this middle line near the left edge. Okay, so we have these different points of view. And then finally, I can look over the now you somehow need everything, I have to raise something. And so if I look over the field of P elements, then E of K is just the set of points x and y modulo P, such that y squared is 4x cubed, well, or the other. P is 2, I should take the original equation. So let's say y squared minus y is x cubed minus x, except that there's one point at infinity. So the number of points of E of k, which is usually called, just called n of p, will be the number of solutions of this plus 1 because of infinity. So it will be 1 plus, in one way to write this, if p is odd, it's the sum x modulo p, and then here you put 1 plus the Legendre symbol, 4x cubed minus 4x plus 1 over p. Because the Legendre symbol of this number, if this number is not a square, then there are no solutions. The Legendre symbol is minus 1, 1 minus 1 is 0, there's no contribution. If this number is 0, then it has one square root, and the Legendre symbol is 0, so you get 1. And if this is a non-zero square modulo p, it has 2 square roots, and so 1 plus the Legendre symbol is 2. So this is almost correct, and of course now the 1 plus, I can just add it up, it's p. So this is an explicit formula in terms of the Legendre symbol, but it's not at all important, but that is the formula. But the most important thing is that we count the number of points modulo p. And so if I do that, that gives me now an infinite number of numbers, but actually it turns out that it's better to write this number. The interesting part is this sum, and actually it's better to put it with a minus sign. So we have a certain number, AP, which depends on p, of course, and it's a famous theorem that AP is, it can be positive or negative, but it's never bigger than 2 squared of p in absolute value. So now, what one does with all of these numbers is to make the L series of the curve. So the L series of E over Q. S is the product, well, to be very precise, it's 1 plus 1 over 37 to the S. That's the 37 that we haven't yet seen, but now you see that it's a bit special. But for every other prime, the formula will be 1 minus this AP over p to the s. But now since it's a quadratic term, which is p over p to the 2s. But for 37, the p term drops out. So this is then written the sum an over n to the s. So that defines the numbers an. So I already have defined ap, and now I've defined an. So by using this information over finite fields, we get this collection of numbers, and I'll give you the beginning of it. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 minus 2 minus 3, 2 minus 2, 6 minus 1, 0, 6. Okay, so we get this new information. And now, finally, I know many of you have seen this, but I want to start at the very beginning. We use this information, so now I can erase this. We use the information modulo p only to produce these numbers ap, and then we put them together in this strange form to define other numbers an. And now there was a conjecture for many, many years with many names, such as Taniyama Vey and Vey Shimura and various other combinations. And then it turned, the Taniyama turned into Taylor and the Vey into Wiles. It became a theorem, and the conjecture, which is now a theorem, is that the sum, well, for this particular curve, or for any particular curve, we can prove it, that if you use these same coefficients and put them into generating functions, the sum an q to the n, but the q you write as the exponential of 2 pi I tau for some tau in the upper half plane, so here's the upper half plane, and here's tau, and then q is a number of absolute value less than 1. This function is a modular form, a cusp form, of weight 2, and now you will see the number that I promised at the beginning, that this whole thing is connected to 37, and level 37. So what that means specifically is that in the given case, that if you take any 2 by 2 matrix ABCD with integer entries, but C is actually divisible by 37, so that's the level 37. So you take such a matrix where C is divisible by 37, then if you replace tau by A tau plus B over C tau plus D, then you can prove, and it's difficult even in this example, but incredibly difficult for the general theorem, this is a very, very deep theorem, you can prove that this transforms in this way, that f of this transform tau is equal to f of the original tau times C tau plus D squared. So the exponent 2 for multiform is called weight, so it's weight 2. The fact that this is only true for matrices A, B, C, D, where C is divisible by 37, that's the level 37. And in this case, so the group of such matrices so the A, B, C, D is such that A, B, C, and D are integers. C is divisible by 37, and the determinant is 1. So I forgot to say, with determinant equal to 1, so AD minus BC equals 1. That group is called gamma 0 of 37, and so this says that F is a multiform of gamma 0 of 37, but actually on a slightly bigger group. You add one more matrix, which is the matrix 0, minus 1, 37, and 0, except that doesn't have determinant 37, 1, but 37, so I have to divide by scalar to make that determinant. If you add this group, then you check immediately that W squared is the identity, and that W times gamma 0 of 37 times W is equal to gamma 0 of 37. So even though this matrix has irrational entries, the union of gamma 0 of 37 and gamma 0 of 37 times W is still a group containing gamma 0 of 37 index 2.
W squared is minus or
Sorry. Yes and no. It is minus that n is a matrix, but when I write this, I'm thinking of the action, this A tau plus B. And so W simply sets tau to minus 1 over 37 tau. And if you square that, then W squared is the identity. But it's true that the matrix squared is minus 1. So that's maybe worth a point.
half the point.
No, that's a full point. It's a good comment, but it wasn't really a mistake. It's just, which world I'm working in. I'm in mine and you're in yours. Okay, so now we have all of the main ingredients, but there were two. This is this Taniyama-Wei, or the Taniyama-Wei conjecture. Now the theorem, sorry, I made a mess with the chalk. I'll take care of it later. This theorem you can state in two completely different ways, and they're not obviously the same. So I want to state the second and show how they're related. This says that these coefficients, remember I defined these coefficients, I was saying that an are the coefficients of this L series, and if n is a prime, then you do what I said, and otherwise you multiply in the way that I said. So for instance, A6, you just multiply A2 and A3, but for square free numbers, it's a little more complicated. So one way to say the Taniyama-Wei conjecture, Taylor-Wiles theorem, is that this L series, the same coefficients an, define the multiple form. But the other way, the other version, is that there's a map from the upper half plane, which I defined, that's called it's meant to be a German H. So this upper half plane that I just drew somewhere, here where tau is, this is called H. You can divide H by the action of this group gamma. So remember, gamma is matrices A, B, C, D, which are either of the form I wrote here, or it's that times this matrix W. And so they act on the upper half plane by A tau plus B over C tau plus D, and there's a map into the elliptic curve. And that's very important, and so I want to explain that briefly. And so there are two ways of doing it. So let me start with the first way. I take my f, which I just wrote. So f is a1 times q. Remember, q is equal to my I tau. And here it's written f is q minus 3q squared minus 3q cubed minus and so on. And now I define a new phi of tau. So this is f of tau. Phi of tau will be, well, 2 pi I for convenience. It's the input for tau to infinity of f of tau prime d tau prime. We prefer I infinity. So you just integrate from your point t, tau to infinity. You integrate this thing. So that means, of course, that the derivative of f is minus, up to a factor 2 pi I, the derivative of f is minus 5. Okay? But now, let's look what happens to this expression. Let's compare what happens if you evaluate phi at a tau plus b over c tau plus d and phi of tau. Well, let's look at this difference and differentiate it. When I differentiate here, I get the derivative of a tau plus b over c tau plus d, that's 1 over c tau plus d squared, times the derivative of f, but that's minus 2 pi I times f of a tau plus b over c tau plus d. And here, when I differentiate, I get just f of tau. But now, because f is a modular form of weight 0, that's 0. And so this difference, phi of the matrix times tau minus phi of tau, is identically, its derivative is identically 0, so it's a constant. And so what we see is that if I take phi of gamma tau, where gamma is this matrix ABCD, in my group gamma, then phi of gamma tau minus phi of tau is simply a constant. But of course, that constant can depend on gamma. But it's a constant tau because its tau is 0. But now I see immediately that if I now do this for gamma prime, and I apply gamma prime to gamma tau, I'll get phi of gamma prime gamma tau minus phi of gamma tau is c of gamma prime. And then if I add the two equations, I'll find immediately that c of gamma times gamma prime is just c of gamma plus c of gamma prime. So therefore, what you find is that by integrating this modular form that I just erased, you get this new phi, and what you find is that phi satisfies this, and c, because of this property, c is a map from gamma to the complex numbers, but it's a homomorphism. And so its image is a subgroup of c, or Sibylle, these all subgroups of c. And, okay, so it's a group, and it turns out, this is a theorem, and it's the general theory, it is exactly the lattice that I told you before. That's why I produced those numbers, omega 1 and omega 2, which were these two periods. Well, another one got erased and one is still there. That was the lattice we used. That's exactly the image set that you will get. So this period that you get by subtracting 5 gamma tau and 5 from minus 5 tau, that thing lies in the lattice. So now, sorry, this is, yeah, that's from gamma. But what does that mean? That means if I take the map phi, that's a complex valued map. Phi, this is a convergent power series. I can actually write this, of course, as a power series. Maybe I should do that. If I just integrate term by term, so it would be minus q plus q squared plus q cubed minus a half q to the fourth plus 2/5 q to the fifth. I just take the coefficients I had before, change the sign, and divide the nth one by n. So that's a convergent power series. So this is a holomorphic function for the upper half plane to the complex numbers. But now, if I now project onto C modulo the lattice, then I'm taking phi of tau, but only considering it modulo the lattice. That because C of gamma lies in that lattice, that means that phi of gamma tau and phi of tau become equal. And so therefore this map factors through the quotient h modulo gamma that we were considering before. And I get a new map, I'll still call it phi, which goes from here to here. And remember, this was isomorphic to E. This map is by the Weierstrass P function. Z descent and the Weierstrass P function of Z, and the Weierstrass, the derivative of the Weierstrass P function. So that's one way to define it in two steps. By first going to C modulo lattice, and then into E. Okay? And that absolutely works. And you can do it on the computer for any given point. And so that's how I found what I wrote before when I drew this point in the lattice. Remember, I had a picture, and I took the fundamental domains. And then I said that the point P0 went to a point which was approximately here. The way that I find those coordinates is I just do this computation for the point in question, and I find it. So that's not quite true. That will come later. And I've lost the eraser. Okay, so that's that, but I want to do it the other way. So the other, I want to use directly a parameterization. So let me do it in a different way. To say that this is true, it's known that this h modulo gamma is an algebraic curve. Here it's called x0 of 37. Actually x0 star, because I added this w. So the claim is that we can go from x0 star of 37 to E of c. But if you think what that means, it means that I can parameterize. Remember, E is pairs x and y, such that y cubed minus y is x, that's right, y squared minus y is x cubed minus x. So the claim is that there exist modular functions So a modular function would be, in this case, holomorphic, might be meromorphic in general. Psi of tau and eta tau in the upper half plane. So modular function means, well, the same for eta, that if you replace tau is in the upper half plane, and gamma is in this group, which was gamma 0 of 37, or maybe that extra w. If you make such a change in tau, you don't change psi, you don't change eta. So psi is going to be a function originally on the upper half plane, but because of this invariance, it's on h modulo gamma, and such that for all tau, eta of tau squared minus eta of tau equals psi of tau cubed minus psi of tau. That's exactly what it means to have a map from here to this curve, y squared minus y is x cubed minus x. But now, it's easy to see how to find that psi and eta, at least numerically. I shouldn't have raised those coefficients, I guess I still have a few from there. Namely, what we have now is two equations. We have this equation, but of course this doesn't determine psi and eta, say it's power series in Q. But it determines one of them if you know the other. But there's a second equation, because when we have this map from h modulo gamma into E modulo C, well, into C modulo lambda, and then into E modulo P of C. On an elliptic curve, there's a unique, up to a scalar holomorphic differential. So here it's very easy. This is Z, complex number Z modular translation, n1 omega 1 plus n2 omega 2. Then obviously dz is invariant, because if you add a constant to z, you don't change dz. So here,
there is a claim, another claim for a point. The equation is eta square minus eta equals c cubed minus c.
This is a 3. Thank you. A point for you. It was a 3, actually, and I corrected it. From here, okay. Thank you. It is indeed a 3. Okay, so on this curve, we have the dx over y, and if you remember, that's exactly, it's maybe still written here. This was exactly how I got this integral, by integrating dx over the square root of 4x cubed minus 4x plus 1. So up to a constant, those must be the same. But here I also have something invariant, because if you replace tau by a tau plus b over c tau plus d, then of course you replace d tau by the derivative, it's a different d naturally, d tau over c tau plus d squared. And so you see that since f of tau changes by c tau plus d squared, this probably doesn't change. So this thing, and this thing, and this thing are all the same up to constants. And the constants are being stupid like 2 pi I. So that's why, when you integrate this dx over y1, when you integrate, you get exactly these two numbers, omega 1 and omega 2. When you integrate dz, you of course also get omega 1 and omega 2. And finally, here when you integrate f of tau, it has to be the same thing. Actually, it's 2 pi I, maybe minus. So up to signs, these are all the same. And so what that means concretely...
Sorry.
Wait, let me just finish the sentence, and then you can ask, because I just want to finish it. What it means concretely is that if you take minus 2 pi I times f of tau, this would be psi prime of tau over again 2 eta of tau minus 1. So we have, in this way, two equations. If I'm looking for psi and eta, the fact that they should be on the curve means that eta squared minus eta must be psi cubed minus psi. But the fact that this differential, which here is dx over y, which is dx over 2y minus 1, as we saw, or maybe there's a 2 somewhere, that when pulls back to this means exactly, when you get the minus, that minus 2 pi I f of tau is that. Sorry.
Yeah, since there are a lot of first and second year students in the audience, I'd suggest to underline that when you write d tau over c tau plus d squared, then the two d's are different.
No, I did say it. I said this d is not that d. I said it. It's like the famous German professor who talked about the most general fourth degree equation, ax to the fourth plus bx cubed plus cx squared plus dx plus e, where e is not necessarily 2.718. But of course it might be. But this d is actually never equal to this d. It's impossible. Okay, this d is an integer, and this d is the Leibniz symbol. Okay, so now if you take those two equations, if you just solve them, it turns out you can solve them very easily. So I'll just tell you the answer, but you can do this on your computer. I mean, I did. That's where these numbers came from. So these two equations, give you an explicit parameterization. I'm writing this because even experts in the field have never, they all know that there are parameterizations, but they've usually never actually seen one, or at least written one down themselves. So here you can just do this. And so you start as an ansatz, the psi of tau, but you can show easily that it has a double pole at infinity. So it starts with a constant over q squared plus another constant over q. And the same for 8, except that's a triple pole. And it in fact starts like this. So you start with unknown coefficients. So you start with question mark over q squared, question mark, known, unknown, 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 and here also you have two equations. And at each stage you have two numbers to compute, two equations, and you just solve the linear equation. So it's completely trivial, and you immediately get these expansions. Now that only gives you the first 10 coefficients, or 100 or 1,000, depending on your computer. This is not a closed form, it's an algorithm. But now to get a closed form, you use, remember I defined modular forms. So on the group gamma, like my group, the modular form of weight k. These are the forms that transform like the f we had before. I shouldn't call it f because I already have an f, f1. And then c tau plus d to the k times f of tau. Okay? And there's a formula for the dimension. In this case, well, k has to be even. And in this case, I won't give you the formula. I have it written down, but it's just a board. The first three dimensions are 1, 6, and 8. So this form can only be the f that we already have. But here it's a four-dimensional space, and there's a computer program. You can just compute the basis of that space. And so now what you do is this. Since f had weight 2, but it started with q, it is a simple 0. Psi has weight 0. It is no weight. There's no c tau plus d. This is weight 0. But it has double pull. So if I multiply psi by f of tau squared, let's call that f4 of tau, then this will no longer have a pull. Because psi starts 1 over q squared, f starts q, and this group only goes to infinity, and infinity is 1 plus, don't worry. And so this thing is now a holomorphic modular form, and of course its weight is 4, because it's 2 plus 2 equals 0. And similarly, if I take 8 of tau times f of tau cubed, that will be an m6. And since we have as many coefficients as we want, and these are finite dimensional spaces, by short computation, you can find which modular form in M4 starts with the right 4 or 5 coefficients. There's 7 coefficients, and here are the first 9 because the dimensions are 6 and 8. And then you identify F4 and F6 in some closed form. I won't write it down if I have it here. And then you take that F4 and F6 and divide by F squared and F cubed. And you'll get sine A. So all of this is algorithmic. And then if you do this on the computer, you will check that indeed this F4 and F6 and F satisfy the appropriate equations to parameterize the curve.
I'm sorry, what about grade?
Sorry?
Short grade.
Already? I haven't said anything yet.
101.
You can't be serious. This is so in the second half of this lecture, I will speak still very slowly, but twice as fast. Is that good? Not good? Okay, I'll do my best. It's that nice. Okay, so now Heegner points, finally. So remember I told you that although the title says in English and in Russian that these points are not elliptic curves, actually they are modular curves. So the modular curve, remember we had our example here, which was the curve x0 star of 37, which was h modular gamma actually being in the point of infinity, and gamma here was gamma 0 of 37, well, I just put index 2, it was this slight extension of gamma 0 of 37 in the example. So this one is called x0 star of 37, but there are many modular curves, just as there are many elliptic curves. One of them is that example. But in general, I have x0 of n for every n, and the simplest is x0 of 1. So let me begin with Heegner points on x0 of 1. So they have another name. These are called the points, usually Cm, the points of complex multiplication. So let me tell you what you do. So here's the theorem. So let's look, for the moment, let gamma, afterwards gamma will be that group again. But for now, let gamma just be the group called SL2Z, which is gamma 0 of 1. So this is all matrices A, B, C, D with integer A, B, C, and D determinant 1. No restriction about divisibility. Then it's well known that, remember I defined modular forms. We have special modular forms. For instance, M4, there are no modular forms of weight 2, but there's a unique one of weight 4, there's a unique one of weight up to a constant of weight 6. There are 2, well, you can see what they are, E4 cubed and E6 squared of weight 12, etc. So these are completely explicit things. E4, for instance, is 1 plus 240 times the sum n cubed times q to the n over 1 minus q to the n. I remind you that tau is our variable and q is always e to the 2 pi I tau. So the statement that this is a modular form, I remind you once again, is that E4 is invariant under tau goes to A tau plus B over C tau plus D up to this famous factor C tau plus D to the 4th. But in the case of SL2Z, we know that the group is generated by just 2 generators, minus 1 over tau and tau plus 1, so the matrices 1, 1, 0, 1, and 0, minus 1, 1, 0. So there are only 2 equations you have to check. And one of them is trivial, because any function of q, e to the 2 pi I is 1, so e to the 2 pi tau is always invariant. So any function that's a power series in q, this is not a power series, but a function of q, will automatically satisfy this. This is trivial, and so there's only one non-trivial statement which one has to prove, of course, which is this one. And similarly, E6 is given by, well, I'll just erase here. The coefficient is different, and the cube has become a 5, but it's the same story. And so another famous function is delta of tau, which is q times the product from 1 to infinity of 1 minus q to the n. The power 24, so this looks very strange. So it's a power series, you first a product and then a series. And then, because this thing you can prove is a modular form of weight 12, it must be a combination of E4 cubed and E6 squared. And by looking at 2 coefficients, just the first 2, we find that the coefficients have to be 1 over 1728 and minus 1, and you get such a, for instance, such an identity. So this is just to tell you or remind you, if you've seen, how such elementary modular forms look. And in particular, we have a famous function, which is j, which is defined as E4 of tau cubed divided by delta of tau. Now, the point is that delta tau is never 0, because q is less than 1 in absolute value, because tau is in the upper half plane. So 1 minus q to the n is never 0, q is not 0, so none of these factors are 0. So delta is never 0, so when I divide, this is still holomorphic in the upper half plane. But now, it is weight 0, because E4 is weight 4, E4 cubed is weight 12, delta is weight 12, so this thing is weight 0, so it's simply invariant under the group. And so if I take my x0 of 1, which is just like x0 of 37, it's h modulo, in this case SL2Z, and I map it, well, sorry, that's actually called y0 of 1, so you have to add a point to infinity. Now it's correct. And now you map it with j to the complex numbers, but again, infinity goes to infinity, so it's actually the projected line. Then you get a well-defined function because of this invariance, and it's an isomorphism, actually, between h modulo the SL2Z and C union infinity. And now comes the theorem. Well, first I'll give 2 special cases. You don't need the general theorem. You can do it by hand. So most of you, or all of you, I'm sure, have seen the picture of the so-called fundamental domain of SL2Z. I don't want to say anything about it. But there are 2 special points. One of them is the usual I squared of minus 1. The other is usually called rho. It's 1 plus I squared of 3 over 2. So I is the 4th root of 1. Rho is the 6th root of 1. And the first things that one finds, well, since I started with 2 little rho, I'll start with rho. At this point, j takes on the value 0. But at the point I, it takes on the value 1728. Now this is actually trivial to prove. If I take this example, let's do it. Let me do that. So I take the transformation equation, I'll do E6, it's faster. So E6 satisfies the same transformation equation as E4, but now with tau to the sixth. So now, if I take E6 of I, then I get I to the sixth is minus 1 times E6 of I. And so you see that E6 of I has to vanish. But then, by the equation that's given here, if E6 vanishes, the delta is equal to E4 cubed over 1728. So E4 cubed over delta is 1728. So I just proved this. And you can prove the other one the same way by taking the equation. See, if I do this for E4, it won't work, because tau to the fourth, I to the fourth is plus 1. So there's no contradiction. E4 of I is not 0. But E4 of rho is 0, by this similar argument. And therefore, if E4 of 0 is rho of 0, then so is its cube, and therefore also this quotient. So J vanishes at 0. That's not a theorem, that's trivial. But these two special cases I just proved. But the theorem is, these are examples. The theorem is if tau is the solution of a quadratic equation, just like in school, but so A, B, and C are some integers, and you solve a quadratic equation. Then, J of tau is always an algebraic number. So let me give a couple of examples. Well, I already gave two easy ones. But for instance, if I take J of 2i, so the fundamental domain I of I, but also 2i, then this number is 8,000. It's certainly an algebraic integer. And there's another example that I didn't learn by heart. If I take J of 1 plus I times the square root of 163 divided by 2, then this number, which I apologize that I didn't learn by heart, but we'll soon see why. It's that. So it's certainly an algebraic number. In fact, it's an integer. In fact, it's a cube. It's a cube of something, but we'll come back to that in a second. Now, you can look at these numbers and say, why did I state such a weak theorem? So let me say it in fancier language that I can put on the board. If Q is quadratic, if tau is quadratic over Q, so if the field extension Q of tau Q is degree 2, then J of tau is an algebraic number. That's the basic theorem. There are many, many refinements, and it goes much further, but this is the beginning, the theory of complex multiplication. It's very simple to prove. And if at the end there's still time for questions, and somebody asks me, I'll say in a minute or two how you prove it. But it's in many textbooks, and it's easy. So we have that, but if you look at this example, you'll say, but why is he saying just an algebraic integer? First of all, this is rational. It's not in Q bar, but it's in Q. And secondly, it's not just in Q, but it's in Z. Well, the answer in general is this is not true. This is always true. It's actually true that it's in Z bar. It's always an algebraic integer. So an algebraic number satisfies a polynomial equation with rational coefficients. By multiplying by a common denominator, it satisfies an algebraic equation with integer coefficients. If the first coefficient is 1, it's called an algebraic integer. J of tau is always an algebraic integer. But in general, it's not an algebraic number. Unfortunately, I had already closed my computer this morning when I wanted to write down an example. So I don't have an example handy for you, but if you, for instance, compute on your computer, well, for instance, if you take I plus the square root of 23 over 2, I can't do it in my head. But this will be, it's an element of a field which is a cubic field. Cubic field, well, I don't have to, it just is cubic over Q. So in this example, you will not get an integer. In this example, the first three examples, so the other examples, remember, were J of rho is 0, J of I is 1728, J of 2i is 8,000, J of this is this big number, but this one is not a rational number, it's cubic. And in general, what happens is this. Yes? There's no 178, 163. What?
No. J of rho is 0, J of I is not.
Oh, here!
Yeah.
Thank you. 1 point for me.
It's a horrible number.
178 is a horrible number. This number, we'll come to this number in a second. Okay. So first I want to say a word about this. I mean, I actually had it written down somewhere, but I won't bother it up. So what is happening? What is happening is this. Remember that to say that it's quadratic means that it satisfies a quadratic equation. Now, when you learn how to solve equations in school, you learn that you have to complete the square and then you get a d, and d is the discriminant b squared minus 4ac. And now you find, I shouldn't have used the same letter, I should have used, excuse me, the stupid, capital A, B, and C, because then you'll find that if you change tau by an element, 8 tau plus b over c tau plus d in SL2z, then you'll get a new quadratic equation with a new capital A, capital B, capital C, but the same discriminant. So this discriminant is an invariant. So if I take a tau, which is this, called the C endpoint, this I already said, next homogenian, a C endpoint is a point which is the solution of such a quadratic equation, then it has a discriminant, d of tau, which is exactly this discriminant. And this makes sense because if you change d tau to tau prime, then you change d to d prime a priori. I mean, a prime, b prime, c prime are different, but d prime equals d. So this discriminant is an invariant. So therefore, if I draw a picture of the upper half plane, modulo SL2z, that means I only need this fundamental domain. Because if I have a point somewhere else, it's equivalent to a point here. Then this point, d is minus 4, the point I, because the equation is I squared plus 1 equals 0, b is 0, a is 1, c is 1, it's minus 4. This point, d is minus 3. This point, 2i, d is minus 16. This point, 1 plus I squared of 163 over 2, it's somewhere up here, d is minus 163. But now you can ask conversely. I choose, you will tell me. Also, this is wrong, I think. Maybe it's 20,000. I think I should have looked up some of these numbers before. I think this is I squared 2, and this is maybe 20,000. I did this by memory. My memory is not good. But you don't get any points because no one knew except me. Okay, so we have, here's 2i, here's I times the square root of 2. Where the discriminant is minus 8, here it's minus 16. But then you can do it vice versa. You can choose a discriminant like minus 8 and say how many points are there with that discriminant. And the theorem of Gauss is that it's a finite number. So h is the class number. If d is such a negative number, this discriminant, of course, is always negative, because otherwise the solution would be real, but it's in the complex upper half plane. So d is negative. This h is always finite. This is the number of points in the upper half plane with a given discriminant. But of course, there are infinitely many points in the upper half plane because you can act by gamma. But if I do it up to the action of gamma, then there will be finitely many. So now what happens is this. H of minus 4 is 1. So I is unique. You can look at all the points you want. You will never find any other point in this fundamental domain with discriminant minus 4. There's only one. And similarly, H of minus 163 is 1, but this is actually the most negative discriminant with class number 1. That's a theorem. But if you take H of minus 23, then there are 3 points. I can't draw them without erasing something. The points will be, one of them is 1 plus I squared 23 over 2. So that solves the equation 1, 1, and 6. So this would be A, B, and C, and you can check that B squared minus 4AC is minus 23, and that point is 1 plus I squared 23. Now, of course, you also have minus 1 plus I squared 23 over 2, but that's equivalent, so I don't count it. Then there's half of this point, which is 1 plus I squared 23 over 4. That one has the form 2, 1, and 3. But it is the same discriminant, 1 squared minus 24 minus 23. Then there's the reflection of that 1 minus 1 plus I squared 23 over 4. That would be the point with 2 minus 1 and 3. But those are the only 3. You can show that these 3 points are the only 3 points which have discriminant minus 23. And so that tells that the class number is finite, it's always finite. Here it's 3. And then the general theorem is that if I take the values, and I wish I'd prepared this example, as I had already put away my computer this morning, so I couldn't. If you take these 3 numbers, let's call them J1, J2, and J3, then the product of x minus J1, x minus J2, x minus J3, this cubic polynomial will have coefficients in Z, and you can compute it explicitly. And so each of these numbers is a cubic irrationality. They're roots of the same equation, and they're conjugate. And this is the full statement of the main theory of complex multiplication in the case of J. So now we can do exactly the same thing for gamma 0 of n. So now we take gamma 0 of n, and I take the same thing, but now I have the Heegner point. So Heegner point is you pick D, And I'll assume for convenience let everything be prime, so I don't have to worry about anything. N is prime, D is prime. It's not important, but it simplifies my life. And certainly I want N and D to be prime to each other. At the very least, if they're both prime, you can just say they're different primes. Well, D is a negative prime, so the absolute value is not N. Pick D, and we assume, so there are two cases. If D is not congruent to a perfect square, I know it's not quite perfect, but I'll do my best. If D is not a perfect square modulo 4n, then there are no Heegner points. You can just forget them. So in every discriminant, D is always B squared minus 4AC. This is always 0 mod 4, and squares are always 0 or 1 mod 4. So every discriminant, actually, in all the mathematics, all discriminants are 0 or 1 mod 4. So this condition, 0 or 1 mod 4n, is automatic when n is 1. So every CN point is a Heegner point if n is 1. But now we have a condition. If it is a square, let's say beta squared modulo 4n, then beta is an integer, but you can think of beta as an integer modulo 2n. Because if you add to beta 2n, or a multiple of 2n, then you'll change the square of beta by multiple of 4n, so it will be just as good a choice. But in general, there are several beta. So if this is true, then you fix this value. So the data for Heegner point is actually a level, n, which originally was 1, a d, which originally was the discriminant, and a choice of beta. So this will be a positive number. This will be a number which is negative and 0, 1 mod 4. This will be a number which is in 2 and z, and they are related by b congruent to beta squared modulo 4n. This is the data. If I do not have this data, I do not have Heegner point. But as I said, in the case when n is 1, then every discriminant is a square, and if it's even, beta is always 0 mod 2. If it's odd, beta is always 1 mod 2. So you can forget beta, it's unique. But in general, there are several choices, you have to fix one. Okay, and now the same theorem is true. Exactly the same theorem is true. Namely, I'll just say in words, if everything is good, and certainly if everything is prime and co-prime, then the number of Heegner points on x0 of n with given d and this choice of beta is still equal to the same class number. It doesn't depend on n. They're exactly, so if d is 23, you can't always take d to be minus 23, because it's not a square modulo every 4n, for every n. But if it is a square and you pick a beta, then you will find exactly 3 points of that discriminant, and I didn't say what they are. The Heegner point now is tau, which just as before satisfies the quadratic equation, just as before a, b, and c are integers. In general, I have to assume they're co-prime, but d is a prime, it's not a problem. They're discriminants, and of course the discriminant should be my given d. But I need two conditions that involve the level. One is a is congruent to 0 modulo n. And the second is that b is congruent to beta, this chosen number, modulo 2n. But then you see everything is good, because if b is beta modulo 2n, then b squared is 0 mod 4n. But that's very good, because d is also 0 mod 4n, and 4ac is also 0 mod 4n, is in this condition. And so the theorem, and this is an elementary theorem, the theorem is if you fix n, you have a discriminant, and you pick the beta, and d is beta squared modulo 4n. Then if you look only at quadratic equations of this form, where a is divisible by n, and b is beta modulo 2n, then two things are true. So this is a set, an infinite set, but on this group, gamma 0 to n, remember, was 2 by 2 matrices, just as before, a, b, c, d. But now where c is divisible by my level n, which was 37 in the example, then you'll find that if you, just as here I said, if you change tau, the d doesn't change. If you change tau to tau prime by such a matrix, and c is divisible by n, so in this group, then also the a will still be 0 mod n, and the new b, so if a is 0 mod n, then a prime will also be 0 mod n, and if b is beta, then b prime will still be beta. So the group gamma 0 n acts on this. And now we claim what I wrote before, is that the Heegner points of discriminant d and this beta in H, modulo gamma, gamma 0 of n, which I prefer to think of as just Heegner points in the upper half plane, modulo gamma 0 of n, or I can write again this phase x0 of n. This set is a finite set of cardinality exactly the class number of d, independent of n and beta, so the same number that we had before, and the same theorem is true as before. If psi of tau, or in our case psi and eta, is a modular function, so if it's invariant for gamma 0 of n, so the simplest example, n is 1 and the function is j of tau, e4 cubed over e delta, remember, was invariant under SL2z. So if I have some other gamma 0 of n and some function, like the sine 8, which were here before for 37, then again, psi of this tau, the CM point, so Heegner point. So when I just number these points, I'll call them B, P, DI, and I goes from 1 up to the class number. I'll just number them in some way. Then the claim is that these numbers are still algebraic numbers, even algebraic integers, if my function is no poles. And what's more, there are h of them, and they together are conjugates, and they're the roots of the equation degree 8. So it's just as before.
What is the conditional psi?
Of course, this conditional psi, which I suppressed. For instance, the psi I had before. The condition is it has no poles, so it's integral in the analytic sense, and its coefficients are in z. It's Fourier coefficients at infinity. And there's also something at other costs, but in my example, there's only one cost. So what I'm saying is not a lie, but I'm suppressing everything that makes it. It looks like a lie to an expert.
No,
I actually told the truth. Yeah, it's of course not.
Without transition to sense, evidently wrong.
It's obviously wrong, but
Like for some sides,
you get 3 points for observing this. If you multiply it by yes, of course. But I was hoping no one would notice, but I failed. Okay, so now I did something absolutely terrible, and not only terrible but stupid. I often do terrible things, well, I often do stupid things, so that's not a proof. I actually remember I wrote this very big number. Well, the last part of it's still here. That very big number, when you see a very big number, you might want to factor it. This was already done by a man called Barrett in 1928, and he wrote a paper, but he never really commented on the fact that all of these factorizations were very, oh sorry, I'm getting the wrong one. It's a different one. This number, I have mentioned already that it's a perfect cube, but it's not a random perfect cube. Every perfect cube, if you write its prime factorization, then all exponents are divisible by 3. But in general, if you have a very large number, like this, 20, 30-digit number, then its prime factors, there will be some very big prime factors. But here, this number is no prime factor bigger than 29. It's all very small prime factors. And similarly, if I take the same number and I subtract 1728, here I could say I'm subtracting 0. And remember, this is j of rho. Here, this is 1728. Remember, that was j of I. Then this again factors remarkably, as in this case, 2 to the 6th times 3 to the 6th times 7 squared times 11 squared times 19 squared times 127 squared times 163. So except for the 163 itself, it's a perfect square. And the first one is a perfect cube. So many years ago, Dick Rose and I proved the theorem, and I'll say nothing about the proof. So this was a little before the other, it's a special case. In fact, and the theorem is, take any two, let's say different discriminants, d and d prime. There are two different discriminants. I'll just do it for j, but there's a similar problem. We'll come to the case for higher end. Then if you take the difference of the Heegner point, so this was the Heegner point here, for the discriminant minus 163. Then this 0 is rho, but rho, remember, was 1 plus I squared of 3 over 2. That would be the Heegner point for minus 3. And in this case, they both have class number 1. So the index I, remember, I goes from 1 to the class number. Read that right, it's PD I from 1 to the class number. Here there's just 1. So in general, if I have two such numbers, then I'll have many differences. And so I could take the product. I goes from 1 up to the class number d. and I prime goes from 1 up to the class number d prime. Because remember, these are algebraic integers, but they're all conjugate to each other. And these are algebraic integers, and they're all conjugate to each other. So if I make this whole product, then this is an ordinary integer, so up to sign, it's a product of p to the something. Every integer has a prime factorization. But our theorem is actually the only theorem I know, I mean other generalizations, but the only kind of theorem, where a number which has, you can give its prime factorization in closed form. You can say exactly which primes occur. I will not give the complete formula, but I'll just say the most important thing, that the only primes, you get only primes such that the prime, and in fact 4 times the prime, divides, I'll put the 4 on the right, it divides the product dd prime minus the perfect square over 4 for some x where this is divisible by 4 and where it's positive. So that's a finite set. They're only, given d and d prime, there are only finitely many x such that x squared is less than dd prime and congruent to modulo 4. And so that gives you a finite list of numbers and only their prime factors enter. So let's take this example. Here I took d to be minus 163, and in this example 1728 is j of I, so d prime is minus 4, and so I have 4 times 163 minus the square over 4, so it's simply 163 minus the square, and you see that indeed in this example, especially if I could find it, maybe you can do it in your, it's probably faster to do it in your head, you see that 163 minus 3 squared is divisible by 11. And 163 minus 7 squared is divisible by 19. And 163 minus 6 squared is divisible, that's equal to 127. And 163 minus 0 squared, that's the biggest it can be because the square can't be less than 0, is divisible by divisible by 163. And so you see that, oh no, I erased the factorization, I'm very sorry, it was 2 to the 6th, 3 to the 6th, 7 squared, 11 squared, 19 squared, 127 squared, and 163 squared, but you get these two. But you see each of these primes, 11, 19, 127, and 163, divides one of these numbers, and there are just a few numbers, 163 minus the square, there are only very few, and the only prime factors that are allowed are these. So we have this very nice theorem, given the factorization of the j function. But as I just told you, the theorem of complex multiplication is much stronger. If you take a nice modular function on gamma 0 of n, for any n, and take the Heegner points rather than just the Cm points, then they will still have the same degree. But now there's no j function, because the j function was defined as the function which gave the isomorphism from h modular gamma 0 of 1, union infinity, to C, union infinity. But in general, if you have some group gamma 0, like our group gamma before, the quotient was, well, the genus 1, it didn't have an isomorphism. So in general, you have that. But now imagine that we're back in the case for elliptic curve. So the Taniyama-Wei conjecture that I mentioned says that every such elliptic curve has a map from x0 of n, and half the time it's x0 star, half the time it isn't. But let's take the case of my basic example I used before the break. Y squared minus y is x cubed minus x, and I gave you very explicitly how you send a point, and I even showed you roughly, it was very quick. The algorithm to compute two modular functions for the group gamma 0 of 37 with the slight extension, such that psi of tau and eta tau are invariant by that group, satisfy this equation. So I gave a modular parameterization, which was called phi, and I gave an explicit formula for it as the sum an over n cubed dn with minus sign. That was phi of tau. Modulo this times. That was one way of looking at there were different. No, sorry, this is a better way. So I've done it. So now I can take these points P, D, I, if D is congruent to a square, modulo 4 times 37, which would be computed as 148. But then I will get these points P, D, I, where I takes on the values I from 1 to h to the class number. And then I can take their phi of di, and those are points on the elliptic curve. And each of these points, by the theorem that I just told you, let's say that d is minus 23, I'm not sure that's a square, but if it were, the class number is 3, then there are 3 points, and each one is defined over that cubic field that I didn't tell you what it was. discriminant 23 times 23, and they're conjugate to each other. But an elliptic curve is a group. And so on that group, I can add up these points. And if I add them all up, then they're still defined over Q bar, but they're now invariant of the full Gauss group. That means that they become a rational point. And so this is the match to Heegner points, and this is now finally the title. This is the Heegner point. I'll call this thing just the Heegner point, HD. Well, it depends really on the beta, but if n sub prime is beta is unique up to side, it doesn't matter which one you take, you just have to fix one, so I'll forget it. So for each discriminant D, which is a square modulo 37, modulo 148, you have to choose the square root, you get such a Heegner point. And now you can actually compute it. So remember, we have these specific points, a few of them are still there. So let me give you just two examples. You just, how you do this, so to speak, numerically. So I have them here on my notes, except again I can't find it. Here, so example, if D is minus 67, this is the largest, the largest in absolute value discriminant except 163 with class number 1. So it's the last but 1. But this is a square modulo. So here I can take beta to be minus 9. So then my D will be minus, well, whatever it is, I can write the point. P, D, comma 1 is only 1 because the class number is 1. Is the point 9 because that's minus beta plus I times the square root of 67 divided by 2 times 37, is 74. So this is the first Heegner, well, it's the only Heegner point in this case. This would be the upper left plane. And so H, D, well, I mean, D is minus 67.
Beta is unique.
This is unique because the class number is 1.
Beta is unique.
But beta is unique up to side because beta squared is minus 67 modulo 4 times 37. Since 37 is prime, beta is plus or minus 9. I pick one of them, minus 9. If I pick the other, you don't want to take them both. You don't want to average. You pick one and take that thing. So I said, I don't want to spend time. Here it doesn't matter because it's gamma 0 star, so I don't need to pick, but in general we need it. I should have just omitted it. So here, now I take phi of this point. But remember, phi was given by this completely explicit formula, which I just wrote a minute ago, 5 tau. This written somewhere is the sum an over n q to the n, where n were these integers which I showed you how to compute. And so we can compute this on the computer, and you get 0.4936, in this case plus 0i. And so if you look, remember we have the lattice, which was gen by omega 1, omega 2, then if you just look at this real number, you'll find that it's congruent to 6 times p0. I also told you that p0 was a specific point. You can also do the same thing with p0. You get minus 0.92959 plus a half, times omega 1 plus a half times omega 2. Anyway, when you do this, then you find that this number is congruent, modulo the lattice, to very high precision. You can prove that it's actually exactly, it's 6 times the point p0. So when I erased it, it was the next point, I think 6.14. But it's that point. So you can find explicitly what these Heegner points are. You just take your computer. First, you solve the equation b squared minus 4ac is minus 67. You make a divisible by 37, which is not difficult, and b congruent to 9. And then you compute the value of phi, which is a very rapidly convergent series. You compute to high precision, and you'll find that this point will be a multiple of p0 modulo the lattice. And so that tells you that here the Heegner point for minus 67 is, since we know that it's in the Mordell-Day group, it has to be some multiple, and it's 6 times p0. And so the theorem that you get is that that this thing is always a multiple. So the theorem in this case would be, well, in this case, if I just take the special case E0, remember I told you that this is Z times P0, then you'll get that for every H where this works, this will be a multiple of P0 because that's the Mordell-Day group, and BD you can actually say what it is. This is a certain multiple form, in the sense that I told you the definition of multiple form, but now it's on gamma 0 of 4 times 37, and the weight, I haven't talked about half integral weight, but the weight is 3/2 rather than 2. So there's a specific multiple form, and it's very well known in the theory of multiple forms, how to construct it from the original F, associated to F, There's another modular form whose left is 4 times bigger and his weight is 3 over 2. And if you take that modular form and compute its Fourier coefficients, which you can do by an algorithm, then you find integers, and those integers are exactly the same integers as the ones that you get when you do this. I mean, I have a table of them. I don't think there's so much point giving you the table. So now let me finally come back to, so that's really about Heegner points. I can get mentioned by theorem. Well, in this case, this would come from the work with, I think, with Gauss and also with Cohen a little later. So now let me tell you briefly what the general story is. Now, sort of being concentrated on examples, how it would look if you just took some n, not necessarily 37. Well, remember that we associated to E. E was my elliptic curve. And the conjecture of Taniyama and Weil, which was proved, says that there's always a map. So you can think of this as tau goes to 5 tau, which is the sum an over n cubed to the n. That's in the notation c modulo lambda, or you can think of psi of tau a to tau, but there's always a map from some x0 of n into E, an explicit map. And remember that they're related by the fact this is a map, phi, and it's given by this formula, and the ANs were the numbers where AP was p plus 1 minus the number of points of the elliptic curve over the field of p elements. And then the ANs in general, I gave you a recipe, and then F is this, you use these ANs to make F and phi, and then F is a modular form on gamma 0 of n, and phi is this modular function. And then remember we had this elliptic, we had this L series, L of ES, which is defined as the sum AN over NPS, which was some product that I won't write down again. But you also have the elliptic, the L series of a cusp form, which is defined with the same formula, with the same coefficients. So the theorem is that given any elliptic curve, there is a cusp form of weight 2 on some gamma 0 of n, which has the same L series, and in particular, that gives you then this modular parameterization in the way I explained. And now remember that the big question in the whole theory is what are the rational solutions? And I told you that it always has the form z to the r plus a finite group. And the finite group, there's an algorithm to determine it for any given case, so I'll just forget about the finite group completely. But the r is what? So the famous conjecture of Birch and Sweden-Wright is still open, and you get $1 million if you can solve it. It's one of the famous millennium problems, which are worth $1 million each. And 6 of them are still open, so you can earn $6 million. But they're easier days. Okay, so the conjecture of Birch and Sweden-Wright has many parts, but the first part says that this rank is the order of vanishing of this L series at s equals 1. So this L series, this sum here only converges in some domain if s is bigger than 2 or 1.5. But you can show that this function exists for all s. There's an easy formula that does that if you know that there's a multiple form, otherwise it's hopeless. So there's a function, and you can draw the graph. So if I do it in our case, oh sorry, it doesn't look like that, it tends eventually to 1, because it's, okay? So if you do this, this is s, and this is L of s, and here's 1, then in this particular case, I don't have the picture with me, you'll find that this L series vanishes at s equals 1, but its derivative does not vanish. So it's a simple 0. So that says that the order of vanishing at s equals 1 is 1. And remember that here the rank was also 1, because this group is simply z times the generator, p0. But there are other examples, for instance, a curve of 5077, the famous one, which is rank 3, and then you can do 3 points, and then if you draw the picture of the elliptic curve, then you'll find that it looks like this. So it has a triple 0, it has a point of inflection there. So, okay, so that's the main part of the conjecture, but the conjecture says more. It says that the first non-zero derivative, so the rth derivative, if it has a 0 order r, its rth derivative is the first non-zero thing, is essentially, well, it's equal to a formula. And the formula is a little complicated to say in general, so I won't bother. I'll just take the case of rank 1. So in the particular special case of the Birch-Sweden-Wright conjecture says if the L series of the elliptic curve at 1 is 0, identically, but its derivative is non-zero. That means that so if the graph looks like this, then it's a simple 0. Then this order is 1, so the rank is 1. Then E of Q has rank 1, which means that it's generated by a single point, P1, which in my case is P0, plus possibly a torsion group, finite group. And now it gives you a formula that says that the derivative of L of E prime is equal to this stupid factor, which I'll admit it's not stupid at all. It contains the conjectural order of the Tate operator, which in our case will be 1. It's the product of essentially two numbers. One of them is the height of that generator, which I explained at the very beginning, and one of them is this real period. So in the case of E0 was my standard example, y squared minus y is x cubed minus x. P1 was my point P0, which was 0, 0. The height I gave you before it was 0.051111, something or other. The L series, I don't remember, of course, why should I? Well, this was the height, 4080 and so on. The L series, well, omega 1, I also gave you the real thing was 2.99345, and so on, and you can compute the derivative to high accuracy. There's some trick to do that, it's not quite obvious, and you get 0.305999773. So you can compute all of these numbers to 100 digits, and then you indeed find that this number is this times this, maybe times 2, I forget, there's maybe a factor of 2, but anyway, the thing comes out, in this example, beautifully. So the general Birdswin's conjecture, in the case of rank 1, gives you this remarkable relation that if there's a simple 0, then there's also just one point. And then the derivative, which is now the interesting variant, is equal to the value of that height, up to the factor which is omega 1. And so the theorem that Dick Rose and I proved was a very general theorem about heights of Heegner points. And so the height, the theorem says, I hope I have it written down here in a well-defined way. The theorem says that in general, maybe I'll assume for E's that n is prime, and D is the discriminant of some imaginary quadratic field, and prime to D, so not divisible by n. Then the height, in the sense that I defined at this Heegner point of discriminant D, is equal, and there's a formula. It's the square root of absolute value of D divided by 4 pi squared. And then the sum, J goes from 1 to the genus. So here we have x0 of n, which is the level. This is a Riemann surface. So this is defined as h modulo gamma 0 of n, union some cost. So I'll just put a bar. So some distance at infinity. It's Riemann surface, that it's a genus. Let's say g0 of n. But actually, I only want the minus part of this. So, okay, so I actually want x0 star then. I want to divide by this extra inclusion, remember, minus 1 over 37 tau, now minus 1 over n tau. So call the genus of that g0. Then you'll have certain cos forms. f1 up to f is genus. In our case, for 37, this genus was 1, and f1 is the f that I told you. But in general, there'll be several f's, and each f, one of them might correspond to the elliptic curve. Each f is what's called a Hecke eigenform. So you sum of these different f's. And then there's a factor that's a little complicated. It's the product of the derivative of L1, and then you have to twist the L series by D. Also at 1, and then you have to divide by the norm of the Peterson scalar product. So let me just say in 2 words what that is. We have our f, which was the sum a n cubed n. Then the L series of f twisted by d. And as remember, the L series of a was just an over n to the s. And then you put the Legendre symbol here, d over n, the Kronecker symbol. So it's a detail, it's some number, some explicit number, and f squared is the Peterson norm. It's the integral over the fundamental domain of f of tau squared times the usual volume, dx dy over dy squared. Okay, it doesn't matter at all. It's also, by the way, up to a factor 2 pi I or something. It's just the product. If f corresponds to an elliptic curve, like in our example, it's essentially the product omega 1 times omega 2. And also this number, we know, is essentially omega 2. And so when I divide, then you get, remember that the Bird-Spin-Dyer conjecture says that L of f prime 1 should be the height of the generator times roughly omega 1. But L of f d1 is a certain integer, I'll tell you in a second which, times omega 2, and f squared is equal to omega 1 times omega 2. So if you cancel everything, you'll see, and there's a square root of d somewhere, you'll see that this exactly agrees with the height of the Heegner point being the height of this generator up to an integer, which is that multiple. So let me write this a little better. So the proof of this theorem is a very, very, very long computation. There's a way to compute heights as an infinite sum over all primes and some real contribution. There's a way to compute L-series and products of L-series called Rankin's method. Each computation in this paper was more than 50 pages. You put together 100 pages of computation. You get a formula for this that's 1 page long. The formula for this, which is also 1 page long. But the two formulas are exactly the same. And so you get this identity. So this was the theorem that Gauss and I proved many years ago, which equates the height of the Heegner point with this. So in our case of 37, then the genus is 1, and it says that the height of the Heegner point, in this case, is up to stupid constant. I'll just stop writing 37 over f squared and omega 1. This thing, remember, is essentially omega 1 omega 2. Here I get L prime of f1. And here I get L of fd. But it's a theorem of Walsperger that L of fd in this case is the second period omega 2 times c of d squared, where c of d is the number I told you, the coefficient of some modular form. And so this one is c of d squared times omega 2. This one, remember, that was the Bird-Spin-Dyer conjecture, but here it's a theorem. It's the height of the generator times omega 1. So the omega 1 cancels, the omega 2 cancels. This can't, I've left out some factors. And so what you find is that the height of the Heegner point is the height of the generator times this c of d squared. So from our theorem, in this case, you could do it in all cases, it's one-dimensional. The theorem shows, together with this theorem of Walsperger, that the height of the Heegner point is equal to the height of the generator times the square of this coefficient, which I didn't quite tell you. I just told you that these numbers c of d are the coefficients of a certain modular form. But actually, the Heegner point itself is equal. In fact, that was the theorem I formulated above, that it's actually equal. And for that, you need a theorem which was proved 2 or 3 years later. This was, I think, 1984. And a little later, with also with Gauss and Conan, who was my student, we proved a more general theorem. I didn't tell you that the height of a point on an elliptic curve is actually the value of the bilinear product of the form itself. You have something a little more general. If you have 2 points on an elliptic curve, they have a height pairing, which is a real number, and it's bilinear and symmetric, so this is an associated quadratic form, and the associated quadratic form is positive definite. But there's actually a height pairing. And so the theorem I proved with Gauss was about the height, and therefore the height pairing itself, the Heegner point. But the theorem with Gauss and Conan together was more general. It said if you have 2 different Heegner points, or 2 arbitrary Heegner points, then, I'll just do it in the case of 37, then you get c of d times c of d prime times L prime of f1 times all of this other stuff. So the point is that what we showed was a refinement. Instead of taking the pairing of a Heegner point with itself, we took any 2 different Heegner points. So naturally, the abstract more del vacuum, here it's one-dimensional, in general it's many-dimensional. Here's one Heegner point, here's the other Heegner point. The original theorem gave the length of this vector. The length squared is the height. The second one gives the length squared of this vector. But the new theorem gives, the first theorem gives the lengths of both vectors. But the new one gives the scalar product. And the formula that I found with Gauss and Conan had the same c of d and c of d primes here. So a corollary was that the height, from the explicit formula, the height pairing of 2 distinct Heegner points squared was equal to the height of one Heegner point times the height of the other Heegner point. But if you have any vector space and you have two vectors such that the square of their scalar product is equal to the square of the length of the first and to the square of the length of the second, well, you know that the square of x and y is x times y times cosine theta. And so this formula just says cosine theta is 1. So theta is 0, or minus, or pi. So these vectors lie on the same line. That's the case of equality in Cauchy-Schwarz. So we have equality in Cauchy-Schwarz. This implies, for any, not just for x0 of 37, where that's obvious, but this implies that all Heegner points in E of Q, this is for any elliptic curve, not just my 37, but the whole rank is 1, they all lie on one line. Because their lengths, the product of their lengths is the same as the square of their scalar product. So that was a remarkable thing, but this is exactly what the Birch-Swinnerton conjectures. Sorry, this is if, well, always. So now let me summarize and then I'll stop. So the summary. On an elliptic curve, and a point on it, we have the height, which is greater than or equal to 0, but it's equal to 0 if and only if P is, well, it's torsion on the elliptic curve. So it doesn't see the Z to the R part. That's a general statement coming from the narrow tape theory. Then our theorem with, then complex multiplication tells you that to every discriminant, and using the modular description of elliptic curve, you have this Heegner point. And the theorem with Gauss gave you the formula that says that roughly the height of the Heegner point is some multiple which you can compute times L prime of F1. And it's roughly this times C of D squared. But then the theorem here said that also the HD all lie on some line in E of Q, I mean modular torsion. But now you see this is not only compatible with Birch-Swinnerton, but it proves it in some cases, but it's exactly what Birch-Swinnerton expects, because if L prime of F1 is 0, then all HD are 0 up to torsion, because by the theorem, the height of the Heegner point is a multiple of L prime. So if L prime vanishes and that happens, then all these points of height 0, then they are 0. So there are no height, and so they're certainly on the line, they're just called the 0 vector. It's not very interesting. But if L prime of F1 is non-zero, then our theorem, this is Gauss, Cohen, and Zagier, implies that all HD lie in a single Z times some P0. There exists a P0. And they're all in multiples up to torsion of a single point. But the Birch-Swinnerton conjecture implies much more. It says that E of Q itself is all multiples of a single point up to torsion. So of course this is a trivial theorem if you know this, but this is still the $1 million conjecture. So if you believe the Birch-Swinnerton conjectures, we all do, then you see that either the derivative of the L series is 0, then by our first theorem on the heights, all Heegner points vanish, and the whole theorem, well, it wasn't a good way to make points. There are other points, but not these. But if it isn't 0, then the Birch-Swinnerton conjecture predicts that the whole Mordell Weil group is one-dimensional. And what we show is that at least all the Heegner points are one-dimensional. They aren't all 0. And in fact, then by later work with Polyvac and the famous Euler systems, you can prove, so that is in fact proved in this case, that then the rank is indeed wrong. So indeed this conjecture of Birch-Swinnerton is now, this was a conjecture in general, in this case using our theorem and using Polyvac's Euler systems, it was proved. So I have told you about 1/3 of what I had planned to tell, but I'll stop, since I went over time anyway. I'm not able to answer, but I'm able to listen. That depends on the question. If they ask me to prove Birch-Swinnerton, I don't know. It depends on the question. I'm willing. Я готов попробовать.
Okay.
И по-русски, и по-английски.
Вопрос.
По-французски,
Язык выбирайте сами, можете по-японски. Айну, Вьетнамит,
You speak very slowly.
1 еще.
1 letter per hour. Very slowly, 1 letter per hour.
No, I can read a book in Japanese, but it's a little faster than that. Not that rapid.
Что, есть у вас вопросы? Или вы удовлетворены?
Все устали, хотят домой. Очень обидно, если нет вопросов, так что надо просто.
Ну, давайте тогда поблагодарим еще раз.
Now, sure, that we should maybe some people do a question.